बता देना। Hello my dear friends, welcome to IMS Academy. How are you? How are your preparations going on? I hope that your preparation is going very good, and last week we met and we did the sessions of industrial engineering, and now hardly 10 days are left for the examination, and I hope that you are in your best phase of preparation. You are revising well. Don't study new things. I know you have been hearing this for a long time, but let me tell you that no need to study new things. Whatever you have studied, just focus on revising it. Don't get disappointed on your less IIMTS marks. You may get anything, but no use of being disappointed. My dear friends, just focus on retaining the things and revising the things. Just give your best, and for helping you. So good evening Thiru, good evening Pragya. So for helping you, we are out here conducting the revision sessions every day, 1 hour each, right? And today, my dear friends, we are going to start with the heat transfer revision sessions, and I am going to start with conduction, right? So my dear friends, the focus of these sessions is not to give you any new questions, not to provide you any new concept, but whatever you have studied, just on a revision basis we are going to do it. So thank you Mr. Sandeep, thank you for the reply. Okay, so without wasting any time, let us quickly go into the conduction. So my dear friends, when you start learning conduction, the first thing is that anywhere, wherever conduction comes, the basic formula, the most basic formula is Fourier's law of conduction. So Fourier's law of conduction. So what is Fourier's law? It is nothing but Q is equal to minus K A dt by dx. So it is the steady, steady state conduction we say. Steady state, that means the constant value of conduction that we say. Steady state, that means with respect to time it is not changing. With respect to time, the heat transfer value doesn't change. So we say steady state conduction value. And what is A? A is the normal area. A is the normal area. Normal area. And what is K? K is the thermal conductivity of the material. Thermal conductivity of the material. Thermal conductivity of the material. And what is dt by dx? It is the temperature gradient. It is the temperature gradient. It is the temperature gradient. You know that when you see conduction, the points that comes to your mind is the medium should be stationary. The medium should be stationary medium, right? And temperature difference should also be there. For heat transfer, temperature difference must be there. So for example, there is a T1 temperature. So in flow of negative gradient only, the heat transfer will take place. So when the slope is negative, dt by dx is negative. The dt by dx is negative. So to make it positive only, we are putting a minus sign so that the entire term becomes positive, right? So this is the Fourier's law of conduction. So this is the Fourier's law of conduction, right? Now my dear friends, the generalized conduction equation. Let us focus on what is the generalized 3D conduction equation. Generalized 3D conduction equation. My dear friends, you know that the formula of Fourier's law that I have written, one thing you are seeing, I have not written any y term or z term. I have written only next term. That means it's a 1D. This formula is applicable by considering that conduction heat transfer is taking place along the x direction. That means it's a 1D case, 1D steady state heat conduction equation that I have written. But you know that temperature may, heat may flow in any of the three directions. That means there may be temperature gradient in all the three Cartesian directions. And also, my dear friends, it may change with respect to time. So there may be spatial effects, that is the with respect to dimensions it is changing, and there may be with respect to time, it is time effect might also be there, transient effect might be there. So I can say that T is a function of x, y, z and t, and therefore we have to remember the, and my dear friends, whatever I am writing over here, you must remember, yes, these are the points which you cannot afford to miss out, right? So what is the most generalized 3D conduction equation? So del by del x kx del t by del x. Now why I am using del? Because temperature is depending on many variables, so d will not be there, del will be there, okay. You know partial differentiation, okay, plus del by del y ky del t by del y plus del by del z kz del t by del z plus q dot is equal to rho c del t by del of small t. So this is the equation, my dear friends, which you need to remember. Yes, you need to remember this equation where kx, ky, kz are the thermal conductivity in xyz directions. Q dot is the heat generation per unit volume. So what is Q dot? Q dot is the heat generation per unit volume. Right. Till here for this equation, I have assumed only one thing. I have assumed only one thing that the material is homogeneous. That I have assumed. The material is homogeneous, that I have assumed. Homogeneous, the significance is the density will be same. The density will be same throughout. Now I am going to assume that the material is isotropic. So when it is isotropic, that means the properties are same in all the directions. So kx, ky, kz will be same as k. So now my equation becomes del by del x k del t by del x plus del by del y k del t by del y plus del by del z k del t by del z plus q dot is equal to rho c del t by del of small t. Small t is the time. Now can you easily take out k from here? No, my dear friends, you do not know that your k might be depending on temperature. K might be a function of distance, k might be a function of temperature, both are same things only. So now we have to assume one more assumptions, that k is independent of temperature. K is independent of temperature. So when k is independent of temperature, that means k is equal to constant when it becomes, then only you can take it out from the differential. So now k you can take it out, and then it will become del 2t by del x square, del 2t by del y square, del 2t by del z square plus q dot is equal to rho c del t by del of small t. So very easily I can write del 2t by del x square plus del 2t by del y square plus del 2t by del z square plus q dot by k is equal to rho c by k del T by del of small t. And this K by rho C, this K by rho C is known as alpha, that is the thermal diffusivity. That is the thermal diffusivity. That is the thermal diffusivity. Thermal diffusivity, it tells the rate of heat propagation. It tells the rate of heat propagation, and its unit is meter square per second. So I can write this as 1 by alpha del of T by del of small t. So this is the equation that students generally remember. The first equation in conduction that students generally remembers is this one. But you have seen that how I have arrived at this equation, from where I have started and from till where I have arrived. And if someone asks you what are the assumptions for this equation, so you can tell that the material is homogeneous and isotropic, and then you can say that K is not a function of temperature, or K is independent of temperature, this much of there. I hope you are getting the point. And from here only the simplification starts. That for example, if they say that the heat flow is a steady one, it's a steady state condition that they're saying, that means it is not depending with respect to time. So the time factor you will make it 0. Then they can say that generation is not there, so Q dot term you can make it to be 0. Then they can say that neither heat generation is there nor unsteady state is there, it is a steady state, so both the terms you can make it as 0. And then they can also add that it's a one dimensional along with no heat generation, and steady state it's a one dimensional conduction. So Y and Z terms can also become 0, and finally you will be left with only one term. So the plane slab case that we study is a very very simplified version of this equation. So let us see that. So now we are going to see heat transfer in 1D steady state heat transfer, I should write steady state heat transfer in 1D without heat generation, without heat generation. So clearly you can imagine that I have said no heat generation, I have told steady state 1D, so all the terms will become 0 except one term, and that is, my dear friends, d2t by dx square is equal to 0. This is the differential equation of the situation that we are going to, that we have in front of us. When you solve this, if you differentiate both the sides, d2t by dx square is equal to, if you differentiate both the sides, so you will be arriving at dt by dx is equal to constant C1. And again if you differentiate, so you will be arriving at T is equal to C1x plus C2. So clearly I can say that the temperature variation is linear in the plane slab. So for example, if there is a plane slab over here, there is a plane slab over here, there is a plane slab over here, the thickness of it is L, there is a plane slab, you can consider this to be your plane slab. This is the area, normal area of heat transfer. This is T1 and this is T2. So heat will flow in the direction of decreasing gradient. So this is the slope del T by del X. And clearly why I have drawn this linear diagram? Why I have drawn this linear diagram? Because I know that T with respect to X I am taking from the left hand side. So T is varying in a linear fashion with respect to x. That's why I've taken the linear. So from here what I can say, that two constants are there, and based on two constants I have two boundary conditions. At x equal to 0, t is nothing but your t1, and at x equal to L, t is nothing but your t2. If you apply all these equations over here, we will be getting one relationship. Are you getting or not? So my dear friends, after applying this, we will be finding the values of C1 and C2. I will substitute over there, and then I will get a relation. So what relation I am getting? Let's see. What relation we are going to get? Let us see. The relation that we will get is t is equal to, now in place of t1 C1, I will be getting this one. And the value of C2 I will be getting is T1. So this is the, my dear friends, the temperature profile that you need to remember. What can be the question? If the question is the temperature at the ends are T1 and T2, which is given as some values, what is the temperature at x equal to for any x value? They can give the question like this. So if you remember this profile, I can very easily put the values and get the answer. So this profile I would suggest everyone to remember, although there are other methods also to get the answer. But don't forget, your major aim is you have to find the value of Q, that is the heat transfer, and whenever the question says steady state heat transfer, so I have only one formula with me. The formula is minus K A dt by dx. Only one formula I have, only one formula. Dt by dx. So when you find dt by dx, so ultimately you know, Q is equal to delta T divided by L by K. It will come out to be delta T divided by L by K. Delta T divided by L by Ka, and this L by K, now see the analogy with respect to electrical resistance. You also know that del V is equal to I into R from your own Ohm's law. So here also delta T is equal to Q into L by Ka. So if you match, delta V is just like delta T, current is flowing, so heat is flowing, so there must be some resistance, so here also the resistance is L by K. So what is thermal resistance? What is thermal resistance? It is nothing but L by K, L by K, L by Ka. And if someone asks you what is the unit of it, so unit will be delta T by Q, whatever is the unit of this. That means the unit will be degree centigrade or watt, degree centigrade or Kelvin divided by watt. This is the unit of thermal resistance. This is the unit of thermal resistance. Are you getting or not? Are you getting or not? So my dear friends, this is the entire scenario of your plane slab. This is the entire scenario of plane slab. This much only you need to remember, not much. This much only you need to remember. Okay. And then my dear friends, you know that what the questions are coming, how the questions will come. How the questions will come? They will give you this slab, then they will give you another slab, slab number 2, and then they will give you another slab, slab number 3. Then they will give you some thickness of this, then they will give you some thickness of this, then they will give you some thickness of this. So let's say the thickness they will give you as L1, the thickness they will give you as L2, then L3, then material conductivity, thermal conductivity K1, this is K2 and this is K3. Then some fluid is coming from here, hot fluid is coming from here. Let's say it is T infinite 1 and H1 is the heat transfer coefficient. Then it is getting conducted. Let's say this is T1 of this phase, then T2 of this, then it is getting conducted, then it is T3, it is getting conducted, and then it is T4 for this, and finally it is getting convected to the colder atmosphere, and it is T infinite 2 and H2. And then among this he can ask you anything. Among this he can ask you anything. For example, he can ask you what is the steady state heat transfer value. He can ask you any of the temperatures, any of the temperature he can ask you. But one thing, my dear friends, you know that heat in convection is given by, heat in convection is given by Newton's law of cooling. Newton's law of cooling, where H is the heat transfer coefficient, H is the heat transfer coefficient, A is the surface area. No, in conduction A is the normal area, over here A is the surface area. And Ts minus T infinite, Ts is the surface temperature, infinite is the T infinite is the ambient temperature, and there is a Q convection. So delta T, again if I have to find the thermal resistance over here, then I have to compare with the electrical analogy. So it will become delta T is equal to Q into 1 by HA. I can write in this way. So what is the thermal resistance over here? So the thermal resistance in case of convection is 1 by HA. 1 by HA. H is the heat transfer coefficient. What is the unit of H? Watt per meter square Kelvin or degree centigrade. Anything you can write, because it is the temperature difference that you are concerned with. Okay. And what is the unit of K? K, thermal conductivity, it is watt per meter Kelvin. Watt per meter Kelvin over watt per meter square Kelvin over here for H. So all these things are there, and this you need to memorize. So I hope no doubts are there till now. Now my dear friends, let us see steady state heat transfer. Steady state heat transfer in case of hollow cylinders. In case of hollow cylinders. So you can clearly see, you know that hot fluid flow through pipes. Hot fluid flow through pipes. So hot fluid flow through pipes. So this is the hollow pipe that you are seeing. This is the hollow pipe that you are seeing. The inner radius I am taking as R1 and outer radius I am taking as R2. Hot fluid is flowing through this pipe, and now I have to take, see, if hot fluid is flowing through this pipe, the heat conduction will be in radial direction. The heat conduction will be in radial direction. So over here, as of now what I am doing, in one direction only heat is conducting, that I am assuming, and that direction is radial direction. So see, earlier in plane slab it was in Cartesian system, but cylinders if you have to represent, it will be very difficult to represent it in cylinder, Cartesian system. It will be very easy to represent in cylindrical coordinates, and sphere it is very easy to represent in spherical coordinates, right? So in cylindrical coordinates r will be there, that's why you don't find x, y, z terms over here. Cylinder, if you represent in x, y, z term, it will be very difficult. So that's why there will be only cylindrical coordinates, and that too only one direction I am considering, in the radial direction. So whatever formula you have, that is for radial direction only, only r will be present. So from here in radial direction heat is flowing, so conduction is taking place in this material, and this is the whose thermal conductivity is K, and only one value it will flow. Why? Because I have considered steady, not that steady state heat transfer will change when it flows across the radial direction. It will be same value. Why? Because we have taken steady. So in this direction it is flowing, and finally it will get convected from the outside ambient. It will get convected from the outside ambient, right? So how is the derivation done? I will consider one, when you go across the radial direction in cylinders, you will find that the temperature is varying with respect to radius. The temperature is varying with respect to radius. So whenever something is varying, we have to take the elemental of that small element we have to take, and all our analysis we will do it over there. We have to take one element. So that's why you take a radial element, a cylindrical element you take, and you do all your analysis over there. So I'm just giving you a hint. I'm not going to do that because we have to remember a lot of things, but I'm just telling you that how the derivation is being done. And when you do the analysis over there, when you do the analysis on that cylindrical small element, so what we arrive is now if I take K constant, from here, so this is the equation that you will arrive at. This is the equation that you will arrive at. This is the equation that you will arrive at. This is the equation that you will arrive at, right? And see, only r term is there. Only r term. Steady state I have told. Steady state, that means no time term will be there. One dimensional I have considered. So only r term is there. That is the radial direction. And now if I say assuming no heat generation, see, this is the equation which you need to remember. This is the equation. Why I am writing this? Because you need to remember this. So now if I say that assuming no heat generation, that is Q dot is 0. So what will be left? 1 by R del by del R of R into del T by del R. You can write with dt also, that is not the issue, but okay. So this is the equation that we need to solve. So 1 by R del by del T R into del T by del R equal to 0. So del by del R, del by del T R dt by dr is equal to 0. So if you integrate, so R del T by del R will be some constant. R del T by del R will be some constant, right? R del T by del R will be some constant. And then I can write dt by dr is equal to C1 by R, right? So from here dt is equal to C1 dr by R I can write, and then if I integrate both the terms, both the sides, so T will be C1 ln R plus C2 I will get. So if someone asks you that in a hollow cylinder, how the temperature variation is there, what is the temperature variation? So you can say it is logarithmic in nature. Temperature varies logarithmically. Right? And again, there are two constants, boundary condition you will apply, that what are the boundary conditions? At R is equal to R1, temperature is T1, obviously you will put over there, and at R equal to R2, temperature will be T2. So when you put these boundary conditions, so you will get a similar temperature profile like the same way we did in plain slab. Here also we will do. So what temperature profile you will get? The temperature profile equation that you will get is this. Again, I will recommend you to remember this equation. I will recommend you to remember this equation. Why? Because the question can be very easily that at R equal to R1, temperature is T1, at R equal to R2, temperature is T2. Find the temperature at any given radius, for example, 2 millimeter or 2 meter, something like this. Although you can do it by other method also, but this is very easy if you memorize. And finally, you know that I have to find Q, and Q you know that whatever case will be there, I am going to use only one formula, that is Ka dt by dr. Only one formula, Fourier's law. Only one formula I will use, that is Fourier's law. So if I write it in that way, if you finally tell me that what equation that we get, that is ln R2 by R1 by 2 pi KL. 2 pi KL del T by this. So why I have written in this form? Why I have written in this way? Because I can very easily find out what is the thermal resistance, and that is ln R2 by R1 by 2 pi KL. This is the thermal resistance, where K is the thermal conductivity of the cylindrical material, L is the length of the cylinder. L is the length of the cylinder. So what is the length of the cylinder? The length of the cylinder is in this way. This is the length. This is the length of the cylinder. This is the length of the cylinder. Are you getting or not? So all these things you need to memorize, my dear friends, and after that you get any question, you will be very easily in a position to solve. Is it clear? Is it clear? Is it clear? So this much only you need to remember. Right? Okay. Okay. Now, my dear friends, we have done plain slab, we have covered cylinders, and now we see conduction in spheres. 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 So my dear friends, I am directly writing the methods, you know, that how an element is taken and then how it is analyzed, and I am directly writing the conduction equation. That is a general conduction equation. 1 by r square d by dr of r square dt by dr plus q dot by k is equal to 0, because I have considered steady state one direction, steady state radial direction. You know, in spherical coordinates r, theta, phi, azimuthal angle, all those angles are there, one more angle, theta and phi. So those angles I am not considering in taking into account, only I am considering the radial direction. Okay. So assuming no heat generation, assuming no heat generation, q dot will be 0. So what you are left with? 1 by r square So I can say d by dr of r square dt by dr will be 0. So if you integrate both the sides, what you will get? R square dt by dr is equal to some constant C1. So dt is equal to C1 dr by r square. If you integrate, t is equal to C1 minus 1 by r plus C2. So what is the variation that you are seeing? The variation that you are seeing is hyperbolically. What is this variation? This is hyperbolically. Inverse relation, hyperbolically. And again, if you two constants are there, so let's say at some R1, at R equal to R1, temperature is T1, and at some R equal to R2, temperature is T2. So what will be, I can get the temperature profile. So what is the temperature profile? So this temperature profile that we will get is, let me write, T minus T1 So this is a temperature profile, and I am telling you that for every, for plane slab, for cylinder, for sphere also I have given you the temperature profile, and I am recommending you to memorize this one. And what is finally Q? That is the steady state heat transfer. That is delta T divided by R2 minus R1 by 4 pi K R1 R2. So what is your thermal resistance over here? R2 minus R1 by 4 pi K R1 R2. It is a thermal resistance. So these are the relations, my dear friends, that I would suggest you to memorize, and see three shapes we have covered already. Plane slab we have covered, cylindrical, and we have already covered what is sphere. So this much only you need to remember, not much. Okay. Now you know that one concept is critical radius of insulation. Critical radius of insulation is there. Critical radius of insulation. So for cylinders, and when we are talking about critical radius of insulation, we are talking about solid cylinders. So for cylinders, critical radius is given by K by H, where K is the thermal conductivity of insulating material, and H is the heat transfer coefficient of ambient. H is of the ambient heat transfer coefficient. So K by H. And for spheres it is 2K by H. So only this much remember. When you were learning the concept of critical radius of insulation, you have done the entire derivation, that how heat transfer needs to be minimized or maximized, and then based on you have differentiated, you have written the conduction resistance, convection resistance, all those things you have done, and finally you have come at this relationship. So when you are studying for GATE, you have to remember the important formulas, right? So K by H, 2K by H is the formula. Are you getting or not? Okay. Now my dear friends, till now whatever formula you have studied, that was for steady state heat generation, steady state heat transfer, conduction in plane slab or cylinder or sphere, but no heat generation we have taken, and then only the profile in plane slab was coming out to be linear in shape. But now let us see that when there is heat generation. So now I am going to teach you or take up this topic, heat generation in plane slab, So d2t by dx square plus q dot by k is equal to 0. This is the equation from where we are going to start. Obviously, I am one dimensional, I am taking into account only one dimensional, and q dot by k, where q dot is the heat generation. So d2t by dx square is equal to minus q dot by k, I can write. Okay. So if you integrate both the sides, dt by dx you will get is equal to minus q dot by k x plus c1 you will get, and then you can write dt is equal to minus q dot by k x plus c1 into dx, and then if you integrate both the sides again, you will get as t is equal to minus q dot x square by 2k plus c1x plus c2. So my dear friends, what is the variation with respect to x that you are getting of temperature? How is temperature varying with x? Temperature is varying in a parabolic manner. Parabolic variation is there. Obviously, two constants you are seeing, and here only you will substitute two boundary conditions, that at x equal to some 0 the temperature is this, at x equal to L the temperature is this, and based on this only you will get the profile. Once you get the profile, you will get whatever they are asking, you will be able to get. And always remember one thing, whatever is the amount of heat generation, that is equal to heat convection from the surface. Whatever is heat generated, that is convected, and that is the main fundamental criteria of saying, one way of saying that the system I have taken, it's a steady state condition I have taken. Are you getting or not? There is one way. What is steady state? This is the steady state, that whatever heat is being generated, that is equal to convected from the outside surface, right? Because if there is no convection, If all the heat generated is not convected, then accumulation of energy will take place. So that you don't forget, and from here only, my dear friends, 3 cases we discuss, that equal surface temperature at both ends, unequal surface temperature at both ends, all these conditions we study. So what are the conditions? Case 1, what we discuss over here? Equal surface temperature at both ends. So suppose at x equal to 0, this is x equal to L by 2, or L I can write, and this is x equal to minus L. From here only generation is taking place. The surface temperature is Ts, and at the center the temperature is T max. From here only heat is going in this direction and in this direction, and finally heat is getting convected. So although there is a relation which many of you memorize, but let us take this L by 2, not L by 2 I am taking. So many of you memorize, so you can memorize, but you should not forget that from where this relation is coming. So finally the relation, the temperature profile is so this is the temperature profile, my dear friends, that T at any x is given. So for example, if you want to find at x equal to 0, so you substitute x equal to 0, so you will get temperature value as Ts plus Q generation L square by 8K, and this is the relation that you generally memorize. Sorry. At x equal to L by 2, so this term will get 0 and you are left with Ts. So at any x it is giving you the relationship. Yes or no? At any x it is giving you the relationship. And then it is, I have taken equal surface temperature at both ends, and then there will be unequal surface temperature at both ends. So when it is there, from where you have to start, don't memorize anything, you just memorize, even you can derive it, but you can memorize this relationship. Whatever boundary condition is there, you just substitute over here, get the temperature profile and just find out whatever they are asking. Okay, I don't suggest you to memorize all the things, my dear friends. Similarly, there is heat generation in cylinders. So obviously it is the equation that you should memorize is 1 by R Now I am not taking Q dot as 0, because now I am assuming that there is heat generation. So when you integrate both the sides, you will be getting r dt by dr is equal to minus q dot r square by 2k plus c1. So r from here dt is equal to, I can write one more thing I can do over here. One more thing, instead of writing this, what I can write? Instead of writing this, cylinder is a symmetric body at r equal to 0, dt by dr is equal to 0. I can use this relation. You can use this relation afterwards also. But if I use this relation, what will happen? C1 will become 0. C1 will become 0, and finally r dt by dr will become minus q dot r by 2k, and I am removing this r from here. Removing this r from here. And finally, if you integrate, so you will get t is equal to minus q dot r square by 2k, sorry 4k, it will become r square by 4k plus c2. So this relationship you can memorize, And then when you substitute the boundary conditions, when you put the boundary condition, the final equation that you will get and that you memorize is this one. Sorry, not 2k, it is 4k. So what this relation is saying? The relation is giving that at any distance r, what is the temperature? At any distance r, what is the temperature? That is the relation is giving to you, right? And clearly you can see that the variation is parabolic in nature. And when you know the temperature, you can find anything. What is the heat convected? What is the heat generated? What is the heat at the surface? Everything you can find. So for example, at surface, what will you do? At surface, you put r equal to capital R. So T will be Ts. And at the center, what you will do? R is equal to 0. So T will be Ts plus Q dot r square by 4k. That is also equal to T maximum. So any temperature you can find out. So these are the things that they will ask in the examination. And also don't forget, my dear friends, that total heat generated will be equal to total heat convected from the surface. Don't forget that relationship. So many questions will be solved from this concept, that total heat generated is equal to total heat convected from the surface. Don't forget this relation. So I can write as Q dot into, what is the volume? Pi r square L, solid cylinder volume formula, is equal to convected HAS, and since the convection is taking place from the outer surface, so 2 pi RL into Ts minus T infinite. I can write this relationship. Yes or no? And finally from here, that the relationship, you want Ts, so it will be, T infinite plus Q gen R by 2H. If you simplify this, you will be getting this relationship. If you simplify this, you will be getting this relationship. But don't forget this one. Don't forget, this concept is very important. From here, so many questions will be solved just like this only, right? So in this 1 hour only, I have discussed the heat conduction equation for plane slab, conduction resistance concept, critical radius, and generation also. So many things we have discussed in this 1 hour only, right? So let's keep it till here for today. Let's keep it till here. 1 hour session it was, and then we will meet next time also with some other chapter, maybe convection or radiation, right? So do revise well. We will be helping you, at every step of your journey, and that's it, right? So take care. God bless. Goodbye.